doing today thermodynamic computing. Yeah, let me just start the I'm gonna start the stream. Go. Created. Let me post about this. All right, cool, perfect. What are we gonna do? First, put some study music, and then second, get started. Basically, we'll do an initial 30-minute session probably. And actually, what I will do is I will create. Wait, we actually have on the post of the hackathon. On the post of the hackathon, we have a link to that actually at the very end. There you go. Yeah, so we're gonna use this one. So we're gonna use these, and we're gonna basically work on it. So there's probabilistic computing intro, essential probability theory, thermodynamics of computing, extropic animation deep dive, processors architecture, algorithms for probabilistic AI, hands-on simulation, and future. It's a long session, so we have time, right? I mean, we're doing these as in preparation for the hackathon as well, to kind of like, yeah, get and dive into the topic a bit more, and then we'll take it from there. Okay, so I guess we'll just learn why we start the shift in certain base computing for efficiency, probabilistic computing intro. I think we'll start with some basics, probabilities. And today we're feeling lunar or galactic. And as I said, hopefully the music base doesn't bother too much. Actually, I should watch back some of the other videos. Let me see. I'll try later. A little less. Yeah, perfect. Let's start the lesson. What do we have here? So we've got multiple chapters. We've got something about the difference between the deterministic algorithm that was previously out and the stochastic one. That's good. So this is, we're really covering the very basics here. Stochastic process, deterministic process. Then we've got chapter 3. Look like. Let's summarize what we've covered so far. Expect a value for a simple algorithm that returns 1 with probability. Yeah, okay. Yeah, it's interesting. It's very the basics, right? So let's kind of like how my noise or hardware errors in real devices limit the reliability of probabilistic computations compared to them. And that's a nice closing question, I think. Okay, so we have an overview here. Cool. Cool. We'll go to chapter 1 first. And again, those are, I think this is relatively simple. So I think the key difference between a deterministic algorithm and a stochastic one is that the deterministic one, basically, given a specific input, you can always know it's always going to give you the same answer, whereas a stochastic one, essentially given the same input, it's always going to give you an answer that belongs to the same probability distribution. yeah, as I said, this is easy. This one's easy. Let's mark it as done. I think I still haven't fixed the bug there, but that's good. That's I think that's nothing new. Uh, Maybe even a bit too basic. Chapter 2 is write down one everyday example of a stochastic process and one deterministic process, then note how probability might affect outcomes in the stochastic case. Let's try to make an example. Let's try to think about an example. Something that is more like an everyday example, not like some process or something, you know, chemical process or whatever. Okay, so first let's start with a classic deterministic example. I mean, it's hard if you think about this, because an everyday example of a stochastic process and one deterministic process. There's always like edge cases for everything, right? There's always edge cases for everything. So in the limit, like everything is stochastic, right? It's like the coffee machine doesn't have to always work, right? But if I constrain it with like enough good conditions, then it's always gonna produce coffee, so to say. What is a 100% deterministic process? You know that I struggle to define a. Okay, I struggle to define something that is fully deterministic without kind of like putting some assumptions on the table. Yeah, for example, if the starting condition is that like if the starting condition is that I'm a healthy human, if I open my eyes, I'm going to all of a sudden see. You know what I mean? Like, I guess. I mean, so something that varies. I mean, making my wife happy. No, something that varies. Yeah, just roll a die, right? So I guess when you roll a die, the result is going to vary, but you know that it's always going to be something between 1 and 6, right? And it's equal probability. So you know that it's going to be within that probability distribution, but it's going to vary, right? But it's kind of like it feels stupid because the deterministic ones, you know. All right. You see, and the same problem we're here. It agrees, Helios agrees, but it's still marked as not done anyway. Because you are flipping a fair coin multiple times could model a simple probabilistic algorithm and what the long run behavior might look like. Okay, so yes, I mean flipping a fair coin multiple times could model a simple probabilistic algorithm, like you know, like the die, like the die example that flipping a fair coin multiple times is a sort of 50-50 chance, right? So it can model. So Flipping a fair coin multiple times could model a simple probabilistic algorithm. Yes, I mean, could you? The thing is, I'm not so sure, right? I mean, could it actually model a useful algorithm? Yeah, I mean, I guess there's utility in that, right? So there's utility in basically being able to produce it's, let's put it this way, there is utility in being able to have something that essentially is a physical representation or digital representation of a probability distribution as a mathematical object. I mean, that, yeah, it's useful. Of course, you can find a utility to these, I guess. Yeah. What sequences of fair coin flips let you generate samples from a simple distribution, and what pattern emerges after many trials? How might sequences of fair coin flips? Are we talking about a single fair coin flip or sequences of fair coin flips? And then the sequences, how, like, are we talking about like running sequences of variable length, or running like an actual any given sequence, and then for many trials, what's the pattern that emerges? What is it you're asking? If you always flip exactly 10 times and tally the heads each run, what pattern of totals would appear after thousands of repetitions? If you always flip exactly 10 times and tally the heads each run, what does it mean? What does it mean to tally the heads? Sorry, bad English. Okay. So if you always flip exactly 10 times, fuck, that is an interesting question. Because 10 times is not too long. And if you do 10 times 1,000 times, it's a different game here, right? Because if you like 10 flips is not that much. 10 flips can easily be skewed towards, like, I don't know, 60-40%, right? And like a 60/40%. And if you do that many times, but okay, I guess because it's the expectation that it's always a 50-50, sometimes it's going to be 60-40, sometimes it's going to be 30-70, sometimes it's going to be 50-50, but ultimately it's really going to be 50-50. I think it's kind of going in the direction of what the expected value is. So this means even if you're doing it just for like 10 times, but you're doing this multiple times, then you're actually going to get that expectation value, which is a 50-50. Yeah. Awesome. I think we can make this one a little more party-like. Okay. Make this one nicer. With an icon, maybe? I don't know. Maybe it's too childish. But it's gonna happen the same. Now it's buggy. I don't know why. I can't. If I mark it, then it just yeah. Oh no. No, it actually worked. Okay. Cool. All right. Chapter 4. Let's summarize what we've covered so far. I mean, so far we've covered something very basic, I would say. So I mean, we've covered the basics of what is the difference between a stochastic and a deterministic process, and the fact that basically the stochastic one is just that you know things at the probability distribution level, right? So that's what you know. You know the probability distribution is going to always be there, but at that distribution. Whereas the deterministic process, you mean that the result is always there. And I don't think I'm insured anywhere here right now. I'm not. I'm sure. I'm sure about everything here. That's a very basic lesson. This one, very basic session. No part feels shaky. It's that maybe, I mean, let's put it this way. So when we talk about stochastic processes, you have probability distributions, and I guess these probability distributions get maybe like they can get complex, right? So it's not just as simple as like a probability distribution over the integers, right? Like I guess you can have crazy probability distributions and even multi-dimensional probability distributions. That's probably the stuff that I need to kind of do some more study on right now. But the basics are clear. That's gonna be an easy, guys, an easy one, easy peasy, easy peasy. Sorry, I don't have a good way to actually keep the chat active. And anyway, let's move on to chapter 5. Calculate the expected value of a simple algorithm that returns 1 with probability 0.7 and 0 with probability 0.3. Now that is the thing, right? So the expectation value is the average of both, right? If I remember well. So, I mean, no. Okay, sorry. It's not the average. It's basically the expected value is the number between. So it would actually be 0.7 times 1 plus 0.3 times 0. I mean, it would actually be. This is where my shaky, like even with this basic concept, but I think the expectation value in this case would be 0.7. Yeah, it is. That's why, because the way you calculate this is because it's the expected value. It's essentially what will be the average outcome. You know what I mean? And I know that the outcome can only be 0 or 1, right? But that's the whole thing with the expected value. This is a little tricky here because it's confusing because you have the boundaries being 1 and 0. But the whole point is it doesn't have to be any of the actual value. Like it could also be more complex. Can you give me? Let's maybe practice a bit. I know I marked it. I can mark it as done, but like here, it's like define a random variable for a given algorithm. This is the expected value. No, I don't need to. No, that's. I think it's more fun to do something like, for example, what would be, and we can ask. Oh no, sorry. Oops. I'm gonna go to Grok. or it's fine. Give me an exercise where the expected value has to be calculated between a three-faced coin of like states 0 or values 0, 1, and 2, and they each have like a specific probability, but it's not equal. I don't know if it's going to give me that exercise. Let's say 0.7, 0.15, and 0.15. And now I think what we would do for the expectation value is basically 0.7 times 0 plus 0.15 times 1 plus 0.15 times 2. Calculator. It's a new calculator. $300 a month calculator. So that's the expectation value. That's the expectation value. Yeah, cool. So it's kind of it's what you would expect. The problem with expectation value is that it's something that makes more sense in the context of a measurement, right? If you're like measuring something, and that's why you're like, oh, what is the value I can expect, right? And when you think about processes like rolling a die or flipping a coin, it's a bit more confusing, because then it's not anymore about measuring. It's something that you kind of know that you can't have values in between, but nevertheless the expected value has a number that is in between, right? And the same book. Chapter 6. How might noise or hardware errors in real devices limit the reliability of probabilistic computations compared? Yes, I mean, that's a good one. So I think the problem with the errors here is that, let's say you have a probabilistic computation that it always outputs 50-50. It's like a fair coin flip, but there's an error that happens. There's a fault in the algorithm, or there's a fault in some of the hardware that makes it basically tilt that result into not having a perfect 50-50, and that's a problem. I think that's exactly like hardware errors actually can cause these probability distributions to not really be the ones that you really want for, and then essentially skew your result towards something that is almost maybe that, but it's not exactly that, and that is a problem. Easy. The first lesson is easy, guys. Oh, we gotta go slow. That's important. How might noise or hardware errors? Oh no, sorry. And what are the main limitations of probabilistic computing you've identified, and how do they connect back to our early examples? I think we're done with this session, guys. I mean, the only limitations that so far I am aware of probabilistic computing is that hardware has to be actually, well, it's the following. So hardware needs to be natively probabilistic, because if it's not natively probabilistic, essentially you're relying on pseudo randomness, right? So the random algorithms that computers have and implement are not real random algorithms. That's one limitation we have not talked about, but I am aware of. And then also, obviously, the hardware is important, that is kind of like fault tolerant, right? Because if it has errors, then it actually influences the probability distributions that your algorithms actually want to operate in. This one was an easy one, guys. Easy. Easy, and we close the session. Yeah. Session complete. Congratulations, you've completed all the steps in your learning plan. End session. And this is again buggy. Fuck, man. Cool. Well done. We should go back to the plan. 22 minutes, 6 probes. Okay, what should I, like, how did I do? Like, you can, like, that's the cool thing. Okay, so I need to change that to the white colors. This fucking ugly the blue ones. Okay, where did I have gaps, brother? Oh, that's not true. Okay. I think we're good, guys. I'm gonna drop it here now. This was the... We've completed this one. That's a bug. This should be now not this number, but anyway. Essential probability theory. Okay, so we're gonna be this is gonna be the nice one. About entropy and inference for computational use cases. The probabilistic one was very simple. Cool, guys. See you tomorrow. I almost think I hear it. I think I hear the baby, but it's fine. I just we've done one session. That's good. Let's start this one. I just want to see what the chapters are. Maybe we should have a chapter overview. It's fine. Architecture. I feel like Mars today. Mars. So what do we have here? We have, what do you think must be true for any probability assignment to be valid and why? We've got 3. Oh, interesting. So stuff we don't know about. Okay. I can see how the actions constrain the possible values when events overlap. Summarization. How would you express the probability of A given B in terms of joint and marginal probabilities? Solve this Bayes theorem problem. These. Nice, cool. So we actually have some fucking practice. That's good. That's good. We've got 8. Nice. I think that's a nice solid lesson. Okay, cool, guys. We can plan for this one. Well, sorry, should have started. Cool. This is a good one. Yep. See you guys around. See you guys tomorrow.